As the last video discussed, graph theory has been a subject and a branch of mathematics that has existed for quite a few hundred years, developed by many different mathematicians, and there was a lot of different theory that kind of came together, which at the time was not necessarily as useful as it is today. Today, graph theory is used for a lot of different things because of the complexity of the street networks in our society and the different types of networks that exist just due to the sheer number of people that we have and the advancements in our technology. But graph theory, as you can read from the slides, is a branch of mathematics defined to be the study of graphs. And these graphs aren't the graphs that you might be thinking of in math, like from algebra class or whatever, where you're doing an XY axis and you're graphing like a sine or a parabola or whatever. Not that that stuff is quite useful, but that's just one type of mathematical graph. But a more typical graph is more akin to the type that we use in geometry, and basically, a graph is just something which consists of dots and lines, which is to typically the graph is supposed to relate or resemble something real. But basically, those dots and lines have specific names, and I wanted to address some of those terms. So the vertices, or singular is vertex. Basically, if we call a point on a graph, that's what we call a vertex, which is the same term we use with parabolas and stuff, but it's a different connotation in graph theory. Um, but basically, in a street routing problem, what we're going to be using the vertices for, which is just a plural of vertex, is to describe the intersections in a street routing problem. And then the streets are going to be lines, right? As we do in a map, right? We have a bunch of so a graph is a little bit different than a map. In a map, we don't typically put the dots, which we're going to be using in graph theory. And there's a reason why. It's because in graph theory, you can't just have lines without the dots, and I'm going to talk about that in a minute. But basically, edges are what we call the lines, and we use them to represent the streets. And basically, it's just a term that we use for the lines in a graph. Like to give you a visualization of what I'm thinking, what I mean here, we could take an example of a street routing problem, like the initial one I set up in the first video, where we're a security guard and we're trying to patrol all of the streets in and around Sunset Cliffs. We could translate all of that information into a simplified version, because in order to solve this problem, the street names really weren't all that relevant. The actual layout of the streets wasn't really important. What was important is, well, how many streets do we have? How many turns do we have? And where are we allowed to turn? And in a mathematical graph consisting of dots and lines, we can kind of understand all of this as well. We have this number of streets represented by the number of edges. So remember, the edge is just a term for each of the lines. And vertices or vertex is the term that describes each of the dots, which in this case would be the intersections. And most maps do not look like this, right? Because most maps are not done in the branch of mathematical study, which is graph theory. But in graph theory, it's all dots and lines, and you can't just have a bunch of lines without dots. So basically, a map like this would not be proper way of doing it in the mathematical sense, which is why we're going to kind of change it to a graph instead. And in graph theory, there's a lot of terms like vertex and edge, which I wanted to talk about a lot of other ones. So in the rest of the video, I'm just going to be kind of jumping into a bunch of different terms and how those pertain to what we're studying. But basically, a vertex set would just describe a set of all of the vertices in a particular graph. So say this is a new graph, which is representative of, this could represent a neighborhood or, a street network or whatever. But this is just another example. But basically, if we're looking at this graph, we have 4 different dots, or again, 4 vertices. And the vertex set would just be a list of each one of those. And we typically describe each vertex in a graph by letter. So notice how they're labeled with A, B, C, D, which is very, very typical and usually how you want to do it. In the previous example, notice I did not label the vertices, but usually you do that in a graph to be able to distinguish them. But here we have A, B, C, D, and our vertex set is just a set of that list. An edge list would be a list of all of the edges in a graph. Basically, what are all the lines? And here we have 1, 2, 3, 4, 5. And as you can see, we describe edges using the 2 vertices that form the edge. So each edge, you could say, well, I could call this edge J and this edge Q, but that's not how it's typically done in graph theory. Typically, the vertices are labeled, and when we do that, we can also label the edges by just using, we don't have to separately label the edges, is what I mean. we can just use the two vertices which make up that edge. And each edge has to have vertices on the endpoints. As I said, you can't have a line that does not have dots at both ends. That's not allowed. So we have edge AB, edge AC. There is no edge AD, but there is BC, BD. We don't need to do BA because that's the same as AB. And you might be wondering, well, which order should I list them in? It doesn't really matter. And you would not want to list both AB and BA because that's the same edge in both cases. And CD. And I forget if I mentioned them all, but we obviously have 5. And so the vertex set, what's often referred to as the cardinality of a set means how many elements are in it, but basically there's four dots, 5 lines, and that describes how many objects we have in each set. Now the term adjacent vertices and adjacent edges just correspond to, as you would expect, vertices that are next to each other. But it's not a positional next to, it really has to do with connectedness. So adjacent vertices are defined to be two vertices that share an edge. So the slides in the packet ask us a couple of questions. Well, are A and B adjacent? Well, yes, they share an edge. They're connected. And that's another way, I think that's a little easier way of thinking about it. Are they connected directly or not? A and C would also be adjacent. Notice, like, if we're thinking about this as a map, those intersections seem like they're a little further apart, and maybe you might not say, okay, are those actually next to each other or not? But, it's kind of taking that question away from it. It has to do with whether they share an edge or not. And also, if I'm looking at the edge list, I can tell if the vertices are adjacent, because if they are, if there is an edge that has them next to each other, they're adjacent. But notice that AD was not an edge and AD are not adjacent. Even though they're kind of next to each other in the position on the graph, that doesn't matter. They're not directly connected. They are not adjacent. And the exact same thing applies to adjacent edges. Adjacent edges are edges that share a vertex, aka connected. So it asks, are A and B, or is the vertex AB and AC, sorry, the edge AB and edge AC, are they adjacent? So if we're looking at that, we've got AB is here and AC is here. Those ones are connected through A, so they would be adjacent. Again, it doesn't really have to do with it. The idea is, are they next to each other or not? But in this case, they are. They are connected together. And you can tell because they both have A within their moniker. And then it asks, are AB and DE, sorry, there is no DE. That makes no sense. I think this is supposed to say DC. Is AB and DC adjacent? So notice that while those two streets are parallel, they're kind of next to each other in a way. That's not what the term adjacent means, because they're not connected together. AB and DC. Notice that they don't share a vertex. So it has to do with more of connectedness. And these terms are relevant when we're defining other terms. Let's get into some more terms. And you might be wondering about, okay, what if all this is important? A lot of these terms are not vitally critical, but they're going to be used a lot. So I just think it's important to at least explore what they mean, because if you're the type who likes to read the book, or if you are getting lost, you want to try to catch up, it's very hard to understand what the book is saying if you don't know the basics. And while these terms are very, very basic, and you can probably figure them out yourself, it helps to just sort of have an overview and talk about why they're relevant and why we care. So to find some other terms, a loop is just as you might expect, is a vertex which connects back to itself. So like if we're looking at this new graph over here, which my face is in the way, let's move me. Notice that, sorry, one sec, I need to fix my laser pointer. There we go. Vertex I, there's a loop there, as we understand to what a loop means, but it connects back to itself, which is a thing. Cool. And you could label that as II vertex. And I'm sure there's a pirate joke in there, but not going to try to make it in this video. Multiple edges would be when two vertices are connected by more than one edge. So if you're looking between J and H, notice how there's two different lines or edges connecting between them. So we just call that multiple edges. And these graphs, this is kind of weird, because if we're thinking about a typical street system, usually you don't have two different streets connected to the same point, right? Because the whole point of a street is so that we can get from one point to another. And why would we build two different roads between them? Or same with a loop, it's kind of strange to try to build a road that just comes back to itself. But if you think about someone like a security guard or a delivering packages is another example we're going to look a lot for why we want to think about street routing problems. These things actually are possible. Like a lot of people have loops in their driveways or something, or sometimes you have like one main road and then another road going right by it, which is, like sometimes they're called a service road, or it's like a secondary road, which is not for as, it's not for traveling as fast. And sometimes you can have two roads like right next to each other. Like in Point Loma, right as you're coming up to campus, right, there's the main road and then there's like the side road for the houses that runs right alongside of it. So it isn't very common, but if you think about it, you can probably find some examples of those things happening. But anyways, why do we care about all this? Is that typically we're gonna assume that our graphs don't have these elements because they're kind of weird. But we often refer to a simple graph as a graph that does not have loops or multiple edges. So this graph would not be simple, whereas this previous graph would have been simple, and the graph from the first illustration would also have been a simple graph. And this one's a little sloppier because you can tell I drew this by hand, but a lot of times it's helpful to take a graph and use a computer to generate, as I did in these other examples, using a computer to generate a graph. And I'll actually show you how to do that too in a little bit. But again, why do we care? Well, sometimes some of the theorems that we reference refer to a simple graph, and if you're like, well, what the heck does that mean? It's important to get through all the terms. So an isolated vertex would be a vertex that is not connected by an edge. So technically, you could imagine that there's another vertex over here. Let's just call it vertex Q, which is not connected to anything. Again, that's kind of a silly example because and if I'm thinking about a street routing problem, when would I have a vertex just floating over by itself? How can you have an intersection without any streets? But what I wanted to remind you about graph theory is not just used for street routing problems. It's used for tons and tons of different things, which is why it's an important branch of math. And most people have basically no experience with this type of math, this branch of mathematics, sort of like from chapters 1 through 4, right? It's a lot of math that most people aren't too familiar with. And that's one of the things about problem solving is introducing a lot of ways of using math in different ways to solve problems. And with chapter 5 through 8, we're focusing on management science. And you can imagine that if you're a manager, say you own a security company, and you want to optimize the way that your people do work, you can see how it's important to try to plan things. And that's really what we're doing is we're trying to organize ourselves by planning. And the term a graph is connected if it has no isolated vertices. So like in this case, this graph would be connected if we did not have that floater that I created. The very last term for this video before we get into the actual math that goes into solving those types of problems is what is called the degree of a vertex. And this one's really important, as you can tell, since I put it in big yellow letters in the slides. Let me move my image now. Well, I'm going to be in the way regardless of where I put myself. But use your imagination. So basically, well, the degree of a vertex is defined to be how many edges are connected to it. So like, for example, if we're looking at vertex A, we have two different edges. If we were looking at the edge list, we had AB and AC. So if we were to count up how many times A appeared in the edge list, it appeared twice. And so therefore its degree would be 2. And notice we can think about graphs in a couple different ways. We can think about them in a very visual way where we're sort of looking at it and seeing how many lines come into A. But you could also think about it in a different way, a more of a quantitative, numerical, or abstract way. We're thinking about the list of edges. You could also determine a lot of these properties from the list of edges as well. And kind of this comparison is what is one of the basic ideas of graph theory. And sometimes looking at a graph in a different way can help us to see ways of solving a problems that we may have not been able to see before. A lot of times in a mathematical statement, we would refer to degree using DEG just for short. So the degree of A would be like a mathematical function, which if we could say the degree of A is equal to the number of vertices coming into it. And I'm going to move the packet in just a second because a lot of these things are on the packet as fill-ins, and I can kind of write in, explain as I'm going from there. But the last couple terms before moving to the packet are, well, is it vertex either even or odd? What is its degree? So basically, an even vertex would be a vertex which has even degree. So like in this case, we said that vertex A had a degree of 2, right? Because it had 2 edges coming into it. That's that. Pretty easy, right? You just count up how many lines you got coming into it. And so since that's an even number too, we'd say that is an even vertex. So A we would call an even vertex. Whereas if we're looking at vertex B over here, notice it has 1, 2, 3 edges going into it, hence odd number. Therefore, it would be an odd vertex. And we could then take a graph and look into what is the degree of every single vertex in classifying. And that's what we're going to do in the packet. So let me swap over to the packet here, which as usual you can print out or look at as well, because this would be what I would have for you guys in class time. So and just to fill in some of these things, I've already discussed them in these slides, but the degree is the number of edges connected to that vertex. Okay, and so if we're looking at these graphs, we already concluded the degree of A was 2, the degree of B was 3. And continuing, we could have another goal of saying, well, let's try to classify every vertex in the entire graph as either even or odd. So C has degree 3, that would be odd. And D has degree 2, which would be even. So as I'm classifying them, A and D were even vertices, whereas B and C were odd. And that 3 is a little bit messy. Let's go ahead and make that better. And say we were to look at the second graph, I could look at, say, vertex E. What I wanted to mention is multiple edges do count for degree. So since it technically is only connected to 2 other vertices, but since this one has 2 edges, this E would technically have a degree of 3. Same with G, have a degree of 3. F would only have a degree of 2. And notice that sometimes you might think of it might be odd to think of this as an intersection because it looks sort of just like a road that has a slight curvature to it. And you might say, well, is this really an intersection or not? But since it's a dot, that's it is a dot. Technically, it's degree 2. But it might seem a little strange in some contexts. But the graph is what it is. It might not necessarily be related to a street rating problem, and there might be a purpose for putting a point there other than an intersection. And in later chapters, we're going to say, well, what does the vertex mean in this chapter? And what does the line mean? They could take on different things. And so vertex J would be degree 4 because it has 4 lines going to it. H would be 4 as well. And I, if you're wondering, does a loop count for 1 or 2? Because technically, if you think about the definition, it says the number of edges. So really, if we were following that definition, you'd say, well, that's really degree 3 because it's only 1, 2, 3 edges. But technically, degree is more about how many edges are leaving it, which even though I kind of wraps around back to itself, if you think about that edge II, that technically is both I. So that's actually 2 degrees. It really counts for 2 in degree. So that I would actually have a total degree of 4, and I would also be even. So if we were to write out all the evens, well, we've got F is even, H, I, and J are also even, whereas odd, we had B, C, E, G, and G as being odd as well. And actually, even and odd is a super critical term, which is why I'm going into it so deeply in this chapter before we move on.